So good afternoon, everyone. Thank you all for joining us today for the latest session in the Dare Hub webinar series. I'm Dr. Chen, a postdoc researcher at the University of Glasgow, working within the Dare Hub. So for those of you who may not be familiar with Dare, Dare is a national hub for a decarbonized, adaptable, and resilient transport infrastructures, brings together UK stakeholders, including industry, government, and civic partners, to explore viable pathways toward a resilient net zero transport system. The hub is funded by UKRI, EPSRC, and the Department for Transport, and involves a collaborative team of researchers from Newcastle, Cambridge, Glasgow, Hereward, and Anglia Ruskin universities. In, in today's webinar, we will be exploring how do the energy and transport systems respond to the extreme events, and what insights can be gained to enhance the resilience, adaptation, and the decarbonization of the transport energy nexus, particularly with the increased electrification. Today we will hear from two expert speakers, and there will be time for audience Q&A after both the presentations. So please feel free to submit your questions in the chat at any time, or raise your digital hand to ask a question after the talks. And also a quick note that this webinar is being recorded and will be uploaded to the Dare National Hub YouTube channel. So please allow me to introduce our first speaker today. So our first speaker is Alexandra Campbell, who has a background in electricity regulation and asset modeling. Alex is currently acting as asset modeling manager at SP Energy Networks in distribution. She has spent 7 years at SP Energy Networks working on long-term investment plans and asset management. Alongside her role at SPAN, Alex is also part-time studying a PhD at the University of Strathclyde, researching the impacts of weather on distribution network assets. Alex is also involved with the Insight Research Hub funded by the UKRI EPSRC. So Alex, over to you.
Thanks. I'll just share my screen now. If you can let me know when you can see it.
Yes, that's perfect.
Yeah, perfect. Thank you. So afternoon, everyone. I'm Alex Campbell. I'm going to be talking today a little bit about resilience to HILP events as an electricity distribution network operator. So I work for SP Energy Networks, or SPEN, which is a distribution network operator in central and southern Scotland, and also in Merseyside, Cheshire, and North Wales. So I'm just going to start quite quickly with showing some of the key electricity infrastructure in Great Britain. So if we start on the top left of this slide, there's electricity generation. So we're starting to move away from large-scale coal and gas power plants, and now there's much more wind farms and other renewable generation sites that are appearing to feed the country. This power that's been generated travels through the transmission network at a very high voltage, which means that we can minimize the losses of the traveling electricity. And then the voltage is slowly stepped down through transformers to get to the distribution network. Sometimes we do get some smaller scale generation on the distribution network. So some examples are smaller onshore wind farms, maybe some quite small solar farms, and then also residential solar as well. So the main dependence on electricity is probably our residential customers, which are fed at low voltage. And they may have electric vehicles, heat pumps, or things like that as we start to head towards net zero, which is going to be increasing customer reliance on electricity. We do have other dependent systems. So I've just named a couple of these on the right of the slide. So the heat network, especially as we're moving away from traditional gas heating. Transport, particularly the rail network, is run by electricity. And as I mentioned before, electric vehicles will be charged through the electrical connection. Telecoms, and then also the water system. So this isn't just water distribution processes, but also the use of water in large industry as well. One of the really key things that I want to highlight here is that the dependency is going in both directions between all of these critical infrastructure systems. So the electricity network needs these systems just as much as they need the electricity network in order to operate safely and efficiently. So I'm going to be talking today about HILP events. So these are high impact, low probability events. What this means is that there's a fairly low likelihood of one of these fairly extreme events from happening. But if they did happen, it's very difficult to predict when they might happen, where, and what the impact could be. And therefore, that can cause quite significant damage or disruption to BAU running of businesses and also to the public. So I've included some examples on this slide of HILP events that could impact critical infrastructure. So just starting with nature, mostly going to focus on this today. So the first one is extreme weather. This could be things like flash floods, heat waves, and then also on the other side of it is large storms will always have a very significant impact, particularly on the electricity network. I think one of the risks of climate change coming through is potentially we're going to start seeing more extreme weather in terms of more frequent and also greater extremes as well, which will obviously have much greater impacts on infrastructure and the kind of daily running of critical systems. Moving on to technology. So I've mentioned there's some reliance on infrastructure already. So the electricity network is very reliant on telecoms. If telecoms went down, it would be very difficult to kind of do the automated running and operation of the electricity network. This would be the same for other technology collapses as well. And a risk that seems to be increasing more and more recently is cyber attacks can lead to cascading impacts across multiple different systems. And then there are some kind of human-led HILP events. So I'm sure everyone remembers the COVID-19 pandemic and the disruption that this caused to daily life. There were also significant impacts on the daily running of the electricity network, and there will have been for other critical infrastructure as well. We've also seen the impacts of recent geopolitical events, impacts on costs, availability of materials, that sort of thing. And then there's also always a risk from financial crises in country and in neighbouring countries as well. You may also spot that I've just thrown in an image of the Heathrow transformer fault on the bottom left of that slide. So that's another example of a HILP event that ended up causing a significant impact and cascading effects for the transport industry. So just thought worth including on this slide here. So in order to minimise the impacts of these events, critical infrastructure, including power networks, electricity distribution, generation, need to build resilience through preparation for these HILP events. So I'm going to talk about one example that greatly affected the distribution network. In November 2021, some of you may remember Storm Arwen hit the UK. This was one of the worst storms to hit in decades. We saw wind speeds of over 100 miles an hour, and this caused significant damage to the electricity distribution network. So within Spain, we saw nearly 200,000 customers lose supply at some point during the storm, which is significantly above normal fault levels. The majority of these faults were caused by trees collapsing onto lines because of the high winds, or things like branches being lifted and thrown onto overhead lines as well, or potentially damaging wood poles. What we saw a lot of during Storm Arwen was multiple faults along a single circuit, which is sometimes called nested damage. So, for example, if you imagine a rural village in North Wales, which is fed from one long overhead line, potentially that could have seen two instances of branches or trees hitting the line, but a couple of kilometres apart. And that would mean that there needed to be multiple repairs, which leads to significant time to restoration for the customers, because operational teams will have to go out and find more than one fault and then fix it. So following Storm Arwen, the GB regulator, which is Ofgem, allowed electricity networks to request funding for additional storm resilience. So this led to submission of what's called a reopener, with multiple initiatives proposed to build on storm resilience and kind of manage that risk as a DNO. A more recent example is Storm Dara, which was just before Christmas in 2024. So this wasn't as widespread an impact as Storm Arwen was, and we found the majority of damage was mostly localised in the northwest of England and North Wales. So again, this saw wind speeds of nearly 100 miles an hour. We saw up to 170,000 customers off supply at some point. However, due to the lessons learned from the few years previous, the Storm Arwen, restoration was actually faster during this storm, despite there being greater levels of localized damage. What this shows is the importance of enhancing our resilience to unpredictable HILP events. And it also shows the benefit and the impact of proactive preparation and learning from past events to mitigate the impact of future events. So we know that a power outage for any length of time can affect dependent systems and customers, but what are some of the cascading risks? So for the telecoms network, this will limit communication, obviously, which can significantly affect not only the public, but also industry. So as we've talked about, the interdependence for the electricity network is that we require comms for network switching, operation, and automation. For the water system, this can impact, a power outage can impact the entire process, including water treatment, sewage, and pumping stations. Alongside this, water is also used in industry for cooling and sometimes used in power generation. So, for example, some renewable generation is hydropower, moving water from one place to another and then generating electricity from that. So there'd be a significant impact on the ability to generate power with no incoming power supply. Looking at the transport network now, so with a power outage, there would be significant disruption to public transport, particularly the rail network. There would also be knock-on impacts on roads and car travel due to traffic lights, street lights, things like that. Also, looking more residentially, due to more customers picking up EVs, there's a greater reliance on the electricity for that. So a power outage would impact the ability to charge and travel on to other locations. So these can all be mitigated through advanced preparation. Despite them being kind of unexpected HILP events, we can build resilience. And this is through things like backup power supplies, such as batteries and generators, plus thinking about where some of these high-risk sites could be. We can prioritize restoration during an outage, or we can start to build in redundant supplies. So instead of having just a single power supply to a piece of critical infrastructure, we can have two feeds. If one goes off supply, at least there is a backup site. And then there's also smarter technology coming out more and more, which will help us to avoid issues with things due to power restoration. So monitoring water flows, water pressure, things like that. So there's no additional cascading impacts following restoration of power. So all this talk of interdependency brings me on to the Ensign project. So as C mentioned, Spen are delivering this project alongside some academic partners. This is an EPSRC funded project, and we're working with the University of Strathclyde, University of Liverpool, University of St Andrews, and Heriot-Watt Uni as well. So this project aims to develop a digital representation of the electricity distribution network, which will allow impacts of other energy vectors and infrastructure effects to be simulated in a safe environment, but based on real network assets. There are 5 work packages for this project. So the first one focusing on the electrical network, and then the others are bringing in the impact of heat, hydrogen uptake, and large industrial clusters, and thinking about that impact on the electrical network. All of these vectors are going to be integrated into a single modelling output, and that will allow assessment of interdependencies and cascading effects as well. So Spen's use cases for the project, they're to enable investigation of future energy scenarios and demand effects, to allow smarter asset management through the ability to identify weaknesses in the network and predict potential outages, alongside smarter resiliency planning, so some of those mitigations that we were talking about before. And also a use case is to enable enhancements for network automation and optimized operation, which all in all is enabling a smarter whole system solution. And all throughout this project, we'll be building the knowledge and skills across academia and within industry as well, to contribute to building resilient systems, not just electrical networks, and also ensure that we do deliver net zero. I think that is all from me. Thank you.
Thank you, Alex, for the excellent presentation on the impact of the extreme events on our electric networks. And so we will take questions from audience after both of the presentations to allow enough time to type the questions into the chat. So let's now move to our second speaker. So our next speaker is Alan Brown, who is the modeling and reporting manager within SSEN's distribution business. His team operate within the DSO directorate and are responsible for medium and long-term forecasting activities that underpin SSEN's load-related expenditure from 132 kV to low voltage. With a degree in electrical power engineering and 10 years experience in distribution industry, Alan specializes in system planning, load forecasting, and regulatory compliance. He previously worked on SSEN's ED2 business plan submission, where he led on load-related investment in the north of Scotland. As a keen petrolhead, Alan keeps a close eye on the automotive sector outside of work and is keen to contribute to the lasting solution of transport decarbonization. So, Alan, over to you.
Thanks, C. Okay, I'm just going to share my screen now. And can you see that? Okay.
Yeah.
Great. Right. Thank you. I can't see questions now. So, yeah. Afternoon, folks. Thanks, C, for that introduction. So yeah, I think Alex did a great job there talking more about the climate change and impact of that. I think when asked to present here, I went down more of the route of impact, increased electrification, more specifically around electric vehicles has on our distribution network, and how we as a DNO and DSO are approaching this from a network resilience perspective. So who are we? We are Scottish and Southern Electricity Networks and the distribution part of that. We operate two DNO licence areas in the UK with vastly different topographies and customer bases. So we supply over 3.9 million homes or customers across the two networks, and it's 3.8 million of those are in the southern licence area. So that does show you just how, I guess, sparsely populated our northern licence area is. And I guess that goes hand in hand with some of the different challenges we face in these areas. One other unique feature of that northern licence area is the amount of subsea cables. So we are powering a number of the Scottish Islands, going as far as Shetland now. And that creates a lot of challenges around resilience in the event that subsea cables start to fall or start to fault. And that again is magnified with the decarbonisation of transport as well, because people rely on the electricity network to travel, as Alex mentioned earlier. So you may be more aware of the term DNO, distribution network operator. You may be less aware of the term DSO, which is distribution system operator. It's relatively new. It's been sort of 5-6 years now, I think, since DSO became part of distribution networks. And really, the difference between a DSO and a DNO is that a DSO is looking more at the operation of the network, much like NESO, or the National Energy System Operator, operate in the transmission network. A DSO functions the same at a distribution network. So we are really looking at the control of power and the balance of demand and generation on that distribution network. The way in which we are using electricity is changing, so we needed to change with it. We needed to have a more complex flexibility market, for example, for customers and consumers to take part in as they transition into electric vehicles, heat pumps, and also small scale generation on the embedded distribution system. So what I'm going to talk about today is, Alex touched on future energy scenarios, which come from NESO, which is more sort of UK-wide scenarios used to sort of create a pathway of credible futures. What we are doing as a DNO and DSO is the distribution future energy scenarios, which looks at that at a more localized level for our license areas. So historically, SSEN looked at the past to forecast ahead, and we would really look at what demand has been doing in an area, and use that historic data to forecast what we think might happen in the future. Where that doesn't work anymore is that we are in a sort of area of unprecedented growth from both transport, from heating, and that new system that we are trying to operate with embedded generation, for example. So looking at the past doesn't work anymore. We need to bear that in mind, what historic trends are doing, but we need to think of a more sort of comprehensive way to forecast forward. So the DFES consists of 4 scenarios, and the latest iteration is based on the 4 FES pathways, which represent sort of ongoing uncertainties and a range of technologies used to forecast ahead. So how do we put this together? So we work with a third party called Regen, who will digest the future energy scenarios published by NESO, and those will have a series of building blocks which may sort of range in. It might be electric vehicles of various different types. It might be solar at domestic level. It might be large scale data centers. It might be a range of different technologies which NESO publish at a UK level. Now that will generally go down to grid supply point level, and what Regen do with support from ourselves and our stakeholders such as local authorities is start to localize that. So a local authority may have a climate strategy to install X amount of heat pumps in certain areas by a certain date. We will incorporate that strategy into our DFES forecasts, and what we end up with is a series of technology volumes or building blocks at bulk supply point, primary substation, all the way down to the LV feeder level, up to 2050. So that allows us to use that information, informed by stakeholders, informed by the GB-wide future energy scenarios, and work with that to produce a load forecast moving forward. So in terms of electric vehicles, we work mainly with EV charger numbers, because you could have a lot of EVs. However, they may not be using the chargers, and it's the chargers that connect to our network, not the EVs themselves. So the FES does not publish EV charger numbers. So what Regen do with us is we will use the EV numbers and a series of spatial factors to come up with a set of EV charger archetypes, as you can see in the screen there. So these include a couple of domestic, so we've got off-street and on-street domestic. We've got car parks, destination, en route, for example, to represent the different types of charging infrastructure that we need to acknowledge and we need to plan our network for. As I mentioned there's a number of spatial factors. This goes into sort of network statistics data, ordnance survey. Regen actually look at where off-street, on-street parking is available and start to inform the DFES numbers that we are given. So how do we do it? So this effectively is a process at a high level, and what my team do. So on the left-hand side there, we get our DFES projections from Regen, and that goes down to number of number of technologies in certain locations. So that's the forward-looking element. What we look at as a baseline for that is the existing demand on our network. So we will pull together data from, it might be the previous financial year that we look at, and we will look at what the monitoring is saying at our substations. So we use SCADA systems, so it could be a series of VTs, CTs on the network to calculate what the demand look like. We will offset generation that's downstream of those monitors so that we get a true representation of gross demand at that substation or asset that we're looking to forecast. So once we've got that baseline load and we've got those defres projections in terms of technology volumes, we will put together the forward forecast using a series of profiles. So it might be quite small on your screen there, but there we've got a workplace EV, so that you can see that sort of peaks at sort of 9 o'clock in the morning. So that would be representing consumers going to an office, plugging in their electric vehicle and charging once they get to work. And we will have a number of these profiles that we're working on a seasonal basis. So these are half-hourly profiles for, say, a representative day in winter, spring, autumn, and summer. And we will model that on top of the baseline data to create a new profile that goes every year up to 2050 for the seasons. And when you start to go into the 4 scenarios, things start to grow arms and legs, especially when you get down to each asset, each LE feeder. So the volume of data here is significant, but it's necessary for us to plan effectively and to ensure our network is resilient moving forward. So once we've got that new forecast, we will build that into, it might be compliance reports that my team publish and put online or send to Ofgem or send to NESO. It might be that long-term constraint analysis, which we'll go into further. Or it might be for cost benefit purposes. Once we've done that constraint analysis, we've identified a problem, we might need that data, that half-hourly profile for flexibility assessments, for example. We might need to go out to customers and say, can you support us by offsetting demand in these areas for X amount of hours in the day, for X amount of days in the year. So we will need that granular data to better inform that decision moving forward. And then ultimately investment papers. So we will need to formulate a business plan and a justification behind any reinforcement that we put together. And that will need to be sent to Ofgem as part of the business plan submission. We're getting better as a business in publishing more and more data now. We don't currently publish these half-hourly profiles for each asset. We will publish the peak data through our network development plan. However, we are publishing the DFES volumes on our website now through our open data portal. So this next slide just shows you in a bit more detail and hopefully a bit bigger on your screen about what this looks like at one substation. So we've got Constable Street primary substation, which is in Dundee. There's not this is more sort of towards the centre of Dundee, so more sort of conventional, commercial area. But you can see there you've got your dark blue baseline data. So we can see there that we've got sort of roughly 12, 13 MVA of underlying baseline demand at that substation. The other colours on top are the various technologies which we've modelled on top of that. So that comes from that DFES those DFES numbers and the half-hourly profiles, and that gives a new picture of what Constable Street demand may look like if in 2030 in the winter and going by that consumer transformation scenario. So we will have these for all of our assets, and we will use this data, as I mentioned previously. You can see there that we've also got the rating of that substation from capacity is 15 MVA. You can see this is just starting to go over that in 2030 by our forecast. So this may be a substation which we need to invest in future, and this data helps us justify that position. So I mentioned the constraint analysis. We talked there about potential need to invest in one substation, but this just gives a bit more of a flavour with my system planning hat on about how we used to do these studies. So you would have your your demand curves, your future demand curves for each of these substations. And this example here is a ring network on our Keith 33 kV network just in the northeast of Scotland. So it's a ring circuit. This is a fault scenario that we've got on the screen here, where that circuit on the left-hand side is switched out, and then you're having to backfeed through that circuit on the right-hand side there. What that's identifying, this is a 2030 analysis, is that you need to invest in those sections of overhead line in order to facilitate that demand in future. So if we think back to the problem here in what impact does increased electrification of EVs have, this is it. I mean, this is the reality of increased electrification, or the potential impact of increased electrification, is that we have to invest in these networks, or we risk the security standards of, we risk breaching the security standards of these networks, and that will result in increased faults. It might result in compliance failures for ourselves, and customers being off effectively, and the issues that can bring as well. So going back to EVs specifically, we've got two vastly different license areas, as I said, and these are really highlighted through these numbers. They're quite striking, actually. We've got around 3% of vehicles in the north of Scotland currently battery or plug-in hybrid, and that number is growing significantly. So that number grew by 50% from 2023 to 2024, going by our DFES baseline numbers. However, those numbers are still quite small, and we're actually behind the national average in terms of license areas. That is a vastly different picture from our southern license area. The percentage is still relatively small. However, we are ahead of that national average in terms of EV growth. And when you look at the numbers, 158,000 last year's DFES to 230,000 EVs currently being driven and sort of owned in our southern license area. So, but you can see on these just where we are in terms of the grander scheme of things in both license areas. And I'll tell you my previous experience looking at large en route EV chargers. You're talking about 4, 5, 6 chargers, essentially equating to small housing estates in terms of levels of demand, and that could cripple networks if we're not aware of this potential change, and looking at smarter ways to operate and manage the demand on our networks. So this is really what I'm struggling with, and I guess the challenge is how do we do this as an industry, not just the DNOs, DSOs, but the consumers, the suppliers, the industry bodies, the government, Ofgem. How do we do this as a collective? And that brings me neatly on to the challenges and opportunities here. So apologies, it is a fairly basic slide, but I think that on the left-hand side sort of shows the challenges that we have just now. So you've got policy changes. One example of that is NESO now being formed, and their role within what's called the Regional Energy System Planner, which is the RESP, and they have been asked by Ofgem to bring a level of consistency across the DFES or FES pathways for all of the DNOs, because at the moment we all do it slightly differently. So NESO are coming in now, and they will have what's called consistent planning assumptions, and that might dictate, okay, that EV profile that I use a different one. And now all the DNOs are using the same one if directed by the RESP. That's great, and I think I'm all for that. But what that might mean is that DNOs that have been fairly conservative with their EV profiles might result in a lot more investment. Is that deliverable? That goes into the investment challenge. Likewise, there might be DNO that have a lot of investment in their plan that now is stripped out because their justification gets taken away because you're using different profiles. They may be a lot lower. So there's challenges with the policy changes coming in from government and from Ofgem that have dramatic consequences on the distribution network infrastructure and how we're going to build it. You've got consumer behaviours, and I've put in there, I'm sure Martin Lewis will thank me for this one, but I've put in there the top electric vehicle tariffs. And this is something that I am struggling with, is how do I start to cater for the amount of smart tariffs? And it's not just electric vehicles, it's just general smart tariffs. But EVs aren't charged at 6 o'clock anymore when people come in from work. EVs are charged mostly in the middle of the night now. So how do I start to work with these tariffs? Start to bed in, okay, well, who's still charging late at night? Who's charging in the middle of the night? Who's charging morning? And how do I manage these different EV tariffs in terms of forecasting forward? So you can see on the far right-hand side there, we've got sort of conventional plug-in at the top. You've got your smart charging profile, or how we've deemed that at the bottom there. And then you've got a mixture. So you've got that 50% smarter profile in there. But we're never going to get that right. And it's always going to be a challenge for us to manage that. We don't know what tariff everyone is on. We're not allowed that information really from suppliers. So how do we sensibly do this moving forward? And that compromise is going to have to be justified with Ofgem for investment purposes as well. And the other one, most of these on the screen here go from sort of 12 o'clock to 5 o'clock in the morning. But there's, I think EDF have got one where you lower your evening peak throughout the week and you get free electricity for a certain amount of hours on a Sunday. How do I begin to do that when I don't know how many people are on this? I don't know how much they're going to reduce their peak by, or how much energy they're actually going to use on a Sunday. So these sort of things are really difficult for us to do, but we need to do that in order to justify our position. You've got data availability, so I think data is pretty key to all of this. If we can't access this data, we can't look at the sort of profiles. We don't have that relationship with suppliers to even inform some of this. How are we going to do forecasting credibly moving forward? And that moves into that accuracy. What is the appropriate accuracy for forecasting 130,000 substations, which I'm doing at the moment? What is that credible accuracy score that everyone is acceptable of? That's something that needs to develop with support from the DNOs and Ofgem. And then you've got market participation. So this is where the development of the flexibility market is coming in now. We as a DSO, we're having to, okay, you've got your peak, which might be over your rating. Should we be procuring flexibility in these areas? Is there enough customers to offset that demand in these areas that we need it? Do they want to contribute? Does it make financial sense for them to contribute? Is the market there? Is the market fair and I guess consistent across the different license areas? So this is really the challenge which we're facing with decarbonisation, with that EV spin on it. So hopefully you've got at least a bit more of an insight into how SSEN distribution are tackling this problem and working with the available data at the moment, and what challenges we anticipate in the future. Okay, thank you.
Thank you, Alan, for that thought-provoking presentation and also the introduction of the SSEN Open Data Portal. And so let's now take a few questions from the audience. I think we got this question for Alex. So while we still have reliance on gas, is there a parallel InSign project for the gas network?
Yeah, so there's not one that I'm aware of. I think one of the work packages that we've got for the Ensign project is hydrogen uptake, which I suppose ties in quite nicely with the gas network. But the reason the main focus is on the electrical network rather than gas is that the importance of the electricity network is continuing to grow. And as we kind of head towards a net zero future, the reliance on gas is likely to stall and go down a little bit. The thing about the electricity network is the assets will remain for a long time. So all the decisions that we're making now are going to impact infrastructure capability in 30, 40, 50 years. So in terms of where the gas network is heading, I don't think it's heading in that direction at the minute. We do consider the impacts of the gas network on the electrical network. Through the Ensign project, we're contacting people like Cadent, other gas networks. But I think as we're looking towards the future, it's really the effect of these changes on the electrical side that's going to be most prominent for us.
Yeah, thank you. And also, I think this question is for both of you. So how are you mapping the peak load by location where the customer behaviors have not been defined? For example, when will the peak time for megawatt HGV charging be, and the cumulative impact of the LGV and the public motorist behavior at the same location?
Want me to go first on that one? I'll give a very brief answer and then let Alan fill in the specifics, if that's all right. So I'm more in the asset management side rather than the load driven side. So don't tend to think about future demand as much, though it is still relevant. I think one of the things we do is we always think about the worst case scenario. So in theory, we don't need to reinforce our network if we could just spread demand out perfectly linearly across every hour of the day. However, in actuality, we can't do that. So that's one of the kind of key things that we need to consider is how much increased demand do we need and how much is flexibility and kind of behavior, as you've said, going to come into it. But Alan, I'll let you expand on that one a little bit.
Yeah, thanks, Alex. And I think yeah, we sort of similar boat. I think we are starting now to think about that in between. Certainly, when you're at optioneering level, okay, how do we look at what customers are doing? And I think to answer this question probably as straightforward as I can is we talk to them. Is what we're trying to do now is we're starting to try and talk to more and more customers to say, okay, well, do you have an idea of what you will be using before you connect on? And do you have a load profile that we can start to use? Because it is difficult, especially for these new technologies that are coming on, to estimate what they're going to do. At scale, we have to make some broad assumptions when you're looking at EVs, for example. We have to look at sort of typical charging profiles and work with other DNOs and maybe some innovation projects that have looked at this in further detail, and we use that to justify our profiles. But for these new connections and these new technology types, data centers, for example, that are coming in, you've got batteries, you're trying to anticipate what they're going to do. And that is difficult because a lot of times batteries, for example, could be participating in a number of different services that might not even be on your network. They might be connected onto the distribution network, but operating a service for NESO. So it's difficult for us, but we need to work with them and speak to them to get as much information as we can. Hopefully that's answered the question.
And do you consider the increased EV charging from local energy production? And also, I think you mentioned that in your presentation, so you consider hydrogen as proposed by the FES scenarios. What is your view on how hydrogen will affect the work of DNOs and DSOs? And how do you integrate new trends such as the probable reduction of investment into hydrogen?
Yeah, so I guess the scenarios which we are working with will have different, I mean, that had a scalar. One of the scenarios is hydrogen evolution, I believe it's called. That is more dependent on hydrogen at, I guess, big at scale, but also at the domestic level as well. So I guess the impact is we will model that. We will model the demand, which may have a much reduced number of electric heat pumps, because we are suggesting that under that scenario, there will be more hydrogen boilers within the homes that will be contributing to the heat network. So that will impact what forecast and what peak demand we see at these substations, because we'll have less electricity demand on that network because we won't have as many heat pumps. So this is how these scenarios fluctuate, not just with technologies, but also with time. One of the scenarios there that doesn't meet net zero is the counterfactual. So we might find that we see the similar level of growth, but it might happen 5-10 years after one of the more ambitious scenarios that we have on our network. So that's how things will fluctuate, and I guess that's the beauty of the data and the way that we're doing it, is we are in control of these numbers. I say that jokingly now, in that we may be told in future by NESO, okay, you have to align to this scenario, and we want all the DNOs to work with that. And that is looking, going by the T3 planning, that is looking like it might be that holistic transition, which has got a good mixture of electricity and hydrogen.
Yeah.
Okay. See quite a lot of questions now.
So we know the importance that because the energy and transportation sectors are the key source of the greenhouse gas emissions. And so with the development of the transportation electrification, the energy and transport system are becoming increasingly connected. I think we got a question for Alex. So for the benefit of the attendees, could you please elaborate on the dependencies of the energy system or those other systems such as the transport system, please?
Yeah, sure. So I think the interdependencies can scale from being incredibly dependent in both directions all the way to a slightly more indirect, but still impactful reliance. So if we look at, for example, the transmission network, the electricity network is highly reliant and dependent on the transmission network, because obviously the majority of power generation is coming through transmission into distribution. Things like the telecoms network, I think I touched on a couple of times in my presentation. It's a very direct reliance that the electricity network has on that. It's used for network operation and increasingly used for monitoring our assets as well. So sending inspection results or load flow 30-minute updates back through as well. In terms of water, heat or gas and transport, I would say the dependence of the electricity network on those is slightly more indirect. So water and heat or gas is very important in the power generation side, but when you're getting down to distribution level, potentially it's not quite as heavily dependent on that. One consideration, I suppose, is things like switchgear manufacture would require water, heat, gas, that sort of thing. If there was a long-standing issue with either of those infrastructures, I think you would end up with knock-on impacts on the distribution network, just in terms of getting access to materials and things that you need. Transport, again, much more indirect, but then the ability for operational teams to travel to sites, to go and find faults, to fix them, and for things like materials, equipment to be delivered to where they need to be. That is a very, very strong reliance on the UK, GB, European, international transport system. So it kind of ranges from that. Without the transmission network, the distribution network would be in trouble, I would say, at this stage in time. Whereas without water and gas, it would need to be quite a long period without them before we would see such a significant impact. but they're all closely linked in my mind. It's a huge interdependent mess, if you ask me. But it needs to be, and I think it will continue to be.
Yeah, thank you so much. And when you mentioned there would be like multi-faults during extreme events, so what restoration criteria or benchmarks, or do you have any like the grid code or similar things are required to meet after a system fault according to some regulatory requirements?
So in terms of when there are storms, it's viewed more like an unexpected event or special circumstances. So in terms of restoration, it's all hands on deck. We have internal policies, strategies to cope with these sorts of events. For restoration, I suppose it depends on where you're going. We have a couple of different license areas, but we tend to focus on safety first most, and then on our customers as well. So all the work that's done for restoration and to get people back on supply, I know particularly if you're off supply for 3 days during a storm, it's going to feel horrendous. And obviously we all work really hard to get the supply restored, but when it's at such scale, it can be very difficult to follow such a prioritized, targeted strategy, which is why we always have reviews after every storm, kind of what went well, what didn't go so well. And hopefully, the more we kind of go through this, we'll be able to build up better and better resiliency and responding policies, codes, things like that. But there's nothing super concrete that comes from the regulator or anything on how we should be dealing with the storm. It's sort of emergency, everyone help where you can.
So the
I
lesson.
can just chip in a little bit more to that as well. I mean, planning networks, we're operating within P2 security or supply standards, so we will look at that in planning our networks. In the north, that is particularly challenging, and we do have a set of sort of delegated substations from P2, because these are very rural areas of the country, and it is very expensive to ensure that security supply standard is met. So that is a challenge for us, in that we may see, okay, you might have one substation that's only got one primary transformer and no backfeeds. What happens when that starts to grow, and with your electric vehicle demand in future, we will need to invest in these areas to bring up that security standard. And that is challenging, because it tends to be that these are areas where it's difficult to run another overhead line or cable out to, and that's the reason why we've not done it in the past. So these are challenging, balancing cost against the security in these very rural areas is something that we work with Ofgem quite a lot on.
Yeah, thank you. So due to time constraints, we just need to take the final question. I think that's for Alan. So in the future, about the large-scale storage of H2 in a multiple energy system, is there much information to date on site selection for optimal H2 storage?
I'm probably not the best or most informed to answer that question. I think when we're looking at hydrogen production is maybe an area where I'm a little bit more informed, and that we may see quite a lot of large hydrogen being produced in somewhere like Scotland. I think, like a data centre, I think it lends itself well to big demand. We see a lot of our network constraints at the transmission level being for export for our licence area. So that's trying to get power down from the north of Scotland, some cases even at Shetland, down to the where the demand is required, and generally southern England. So how do we do that, and how do we mitigate or limit those constraints that we have on that transmission spine down the country? One way to solve that is by big demand in the north of Scotland, and that might be hydrogen production. And I think we're starting to see some of those coming through now, and producing hydrogen in the north of Scotland. So I'm afraid not too up to speed on the storage of hydrogen, but I think that large scale hydrogen production may play a part in north of Scotland.
Great, thank you. So I think we will have to wrap up here. We got really great, fantastic questions from our audience, and a huge thank you again to our speakers, Alex and Alan, for sharing their expertise, and to all of you for joining us today and participating so actively. So we hope you are leaving with new insights into how the energy and transport systems can evolve to meet the challenges of the changing climate, especially in the context of the increased electrification and the decarbonization. And if you enjoyed today's webinar, we warmly invite you to visit the Dare Hub website, where you will find details about our monthly webinar series and the upcoming events. And so thank you again, and have a great rest of your day.